In Lecture 8, we developed a couple different queues using arrays. And while that works and is commonly used, as was mentioned, there's a limitation presented by the fact that the underlying data structure there was an array. Arrays have a fixed size, and if you don't start out with an array that's big enough, you could get in trouble because you don't have enough memory, enough room in the array. All right, well, linked lists is one of several alternatives that addresses that problem. So as I say, linked lists can be used for queues, which would include FIFO queues and stacks, and there are other uses for linked lists as well. A very fundamental aspect of linked lists is the idea of dynamic memory allocation. Okay, well, whether or not you're familiar with the phrase, this is something that you've used as a C++ or Java programmer, because every time you use the keyword new to create memory for some object, you're actually your program is taking a little time out to request more memory from the operating system. And this idea of building new objects and allocating more and more memory dynamically as the program executes is central to linked lists. Okay, so that's quite different than the situation with storing data in one fixed array. Even if you create that array dynamically, once you've created, you have a fixed amount of memory there. And as we discussed, if you wind up incorrectly predicting how much memory your FIFO queue requires, then you'll run out of memory. Okay? But if you build a FIFO queue using a linked list, the situation is very different, and every time you need to add something new to the FIFO queue, you will use dynamic memory allocation to create a little bit more memory, and this will work, and you'll have plenty of memory as long as there's memory available inside your computer and the operating system is willing to give it to you. You won't have to worry in advance about predicting how much memory your program needs. So what happens is that instead of storing the data in consecutive memory locations inside an array, what happens is that the data gets put inside objects known as nodes. Okay? And these nodes can be scattered throughout memory. They don't have to be contiguous. They don't have to be physically close together. Instead, there's a mechanism that is going to link these nodes together in a logical way. Okay, I want to begin by thinking about links conceptually. We'll eventually get into some nitty-gritty code, but it's going to help to discuss linked lists in a conceptual, visual kind of way first. Once again, a linked list is going to be created by logically stringing together a bunch of objects referred to as nodes. And these nodes are generally scattered throughout memory. They're not in any way physically connected. So to pull this off, the way this is done is that each node contains a little extra information. Besides the data that's being maintained, the node also contains the memory address of the next node in the linked list. Okay? So if you've studied C++, students may have studied pointers. Well, that's exactly what we're talking about here, pointer data. And a pointer inside one node points to the next node. Okay, basically contains the memory address for the next node. Okay, now in Java, it's more common to say that an object has a reference that refers to another object. And that's okay. Essentially, it's all the same thing. And I want to be very clear about something here. We're not going to get into the nitty-gritty of pointer syntax and so forth. And so you don't want to worry about the fact that you may not have the background in that. So as I say, you don't have to worry too much about this pointer / reference business here. I want you to, when you see the actual code, I want you to think a little bit about the syntax and so forth. But I don't want you to get too worked up about it. You're not going to be held terribly responsible for that. So longer term, I think eventually you should learn to understand pointers and references in greater detail. Okay. A linked list requires that each node contain a pointer to help find the next node in the linked list. But it can also be useful to have an extra pointer in each node to help locate the previous node in the linked list. Okay? So actually that's the type of linked list that we're going to be dealing with here. I'm going to assume that every node contains 2 pointers, a next pointer to find the next node, and a previous pointer to find the previous node. So this type of linked list that we're describing, where each node has a next pointer as well as a previous pointer, is referred to as a doubly linked list, right? Because you can move in either direction. And that's the sort of linked list we'll be using, but I'll usually just refer to it as a linked list for brevity. Okay. So a nice thing about this is that when we create new nodes, they can be easily inserted into the linked list, either at the beginning or at the end, or even at positions in the middle somewhere. Okay? When you want to insert a new node somewhere, it really just amounts to changing what the pointers are pointing to. Okay, as we'll see. We'll get into some examples of this pretty soon. Okay, it's also nice that we are able to remove nodes. So removing a node from, say, the beginning of the linked list or the end of the linked list, or frankly any node in any node anywhere in the linked list is really just a matter of changing pointers again, and so it can be done quickly. So each node in a linked list is in reality an object, and okay, to facilitate things, it's going to be useful to add one more object. Okay, we're going to add an extra object to this group. This new object is not from the same class. It is not a node. Instead, this new object is going to be something that represents the entire linked list. Okay, it represents the linked list as a whole. The way that I'm going to hook this up, this new object that represents the entire linked list is going to contain two pointers, and one of the pointers is named first, the other pointer is named last, and you can guess that the first pointer is used to locate the first node in the linked list, and the last pointer is used to locate the last node in the linked list. So here we go. Finally, we get to a picture that I've been anxious to present here. So the following figure is a conceptual view of a linked list of numbers. Okay, a doubly linked list of numbers. Okay, I deliberately scattered these yellow boxes around. Each of the yellow boxes represents a node in a linked list. And I scattered them about to emphasize the fact that they could really be scattered throughout memory in a rather random way. Okay? But the pointers that the nodes contain logically connect the nodes into a chain, right? Okay, so let's start with the object, the green box here, which is intended to be the object that represents the linked list as a whole. Okay, it contains a pointer to help find the first node in the linked list. It also contains a pointer to help find the last node in the linked list. All right, let's follow the pointer to the first node in the linked list. The data contained inside that node is simply the number 8. Okay, that node has a next pointer to find the next node in the linked list, which happens to be the node up here that has the data 5 inside it. And if we follow its next pointer, we arrive at the node that has the data 7 inside it. And the next node after that is the node that has the data 2 inside it. And the next node after that is the node that has 3 inside it. And then, if you notice, there is no next node pointer for that node. Okay, we say that that node's next pointer is null. Okay, and because it's null, we conclude that must be the last node of the linked list. It also happens to be the node that the linked list object is pointing to by means of its last pointer. Right, so I hope that's very clear. Moving in a forward direction, we started at the linked list object. We followed its first pointer to the first node in the linked list. Then we just kept following next pointers until we got to the last node in the linked list. Okay? Now, because we've this up as a doubly linked list, we could do exactly the same thing in reverse. We could traverse through this linked list in the opposite order, right? We can start at the linked list node, and following its last pointer, we arrive at the last node in the linked list. Using its previous pointer, we get to the node before that. Using its previous pointer, we get to the node before that. Using that previous pointer, we get to the node before that. And using that one's previous pointer, we get to the first node in the linked list. Okay, and of course the first node has a null previous pointer. We pretty much talked through all of this. Remember that pointer doesn't point anywhere. It's said to be a null pointer. Okay, so the first node has a previous pointer that is null. And likewise, the last node has a next pointer that is null. As was said earlier, if we want to insert a new node, then we're going to have to change a bunch of pointers. The same thing is true if we want to remove a node. Okay, so let's take a look at this example. Let's see what happens if we remove the last node in the linked list. Okay, so it has to wind up looking like this. All right, well, I've actually removed from our view the node that we're taking out here. Let's not worry about it. It's not going to be logically connected to this anymore. Okay, because we're going to reset the last pointer in the linked list object and set that last pointer to point to the node whose data is 2, right? And we're going to set its next pointer to null. Okay, now that it's become the last node in the linked list, its next pointer must be null. And that's it. Okay, we've effectively removed the last node from the linked list. Let's try to take a node out somewhere in the middle of the linked list now. So let's say we go ahead and we'll remove the node whose data value was 7. Okay, and we have to wind up in this situation. All right, so we have to change some previous pointers and some next pointers, and then there it is. All right. When people get messed up doing this kind of thing in actual code, it's really because they're not careful enough, honestly, to visualize what's going on here. It can be very helpful to draw pictures like this. Well, we have two really different approaches to storing data in a linear fashion, right? And one way is to use an array. Okay, an array is basically a sequence of data. A linked list is a very different way to store a sequence of data. Okay, and we talked a little bit about the relative advantages and disadvantages, but let's spend a couple slides going over that here. Okay, so we've actually mentioned this. Adding a new node to a linked list is rather straightforward. We can extend our list of data. In the case of a linked list, that's pretty easy to do. As long as we don't run out of memory, as long as the operating system provides us with more memory, we can keep expanding dynamically the linked list. And that's very different than with an array, where once you've created the array, that's all the memory you've got for the array. Okay? Use that keyword new many times in your Java or C++ program to create new objects. Okay? And you may or may not have been aware, it's such a casual thing to do, you might not have been aware of just what's going on there. When you do that, your program takes a little time out, interacts with the operating system, and if all goes well, the operating system allocates some additional memory for your program. Yeah, here again is this idea that if we want to add some new data somewhere in the middle of our list of data, that can be done very quickly with a linked list. Once we know where we want to put the data, we can just add a new node to a linked list somewhere in the middle by manipulating some pointers. Okay? Whereas with an array, we'd have to shift a bunch of data around, right? As we saw with insertion sort. So those are basically so far making the case for linked lists as the more desirable approach. But there are a couple things to say against linked lists and say in favor of arrays. Yeah, this business of dynamically allocating memory by using the keyword new, creating new objects, these new nodes, it's actually time consuming, and if you do it too much, you'll get a noticeable slowdown of your program. Okay, so that's certainly a negative thing against linked lists. Another thing that arrays have over linked lists is this ability to, sometimes people say randomly access. Using indexing, it's possible to go anywhere we want inside an array. So what I'm saying is, suppose we know that we want to get access to the entry in position 123. 123, that would be the 124th piece of data. The 124th piece of data would be in position 123 of the array. And if we knew that we wanted that piece of data, we can easily access that data by means of indexing, right? Array bracket 123. There it is. There's no such capability for linked lists, right? If you want to get to the 124th entry in a linked list, you're going to have to start at the beginning of that linked list and navigate your way there by following 123 different pointers, or if you include the original pointer from the object that represents the linked list as a whole, I guess it's 124 pointers. Right. So that's going to take a long time. All right, if you wanted to get to the 57,000th node, then it's going to take quite a lot longer. Nevertheless, people in designing software have to trade off the pros and the cons, and oftentimes they opt for a linked list approach as opposed to an array approach. So I want to point out here that some of the basic data structures that we looked at in the previous lecture, namely FIFO queues and stacks, can be easily implemented using linked lists, right? Basically on the back of linked lists. If you have linked lists, you can hook them up to work like stacks or FIFO queues, right? Because after all, you can insert at either end of a linked list, and you can remove from either end of a linked list. I'm assuming a doubly linked list here. Okay, so The code for the linked list at the course site is bundled with the code from the previous lecture on stacks and FIFO queues. If you haven't already downloaded that code and gotten it running, then please do so and take a look at the code. Try to take a careful look at what the test code is doing here, right? There's some comments, and you should be able to make some sense of what is going on by looking at the comments, looking at the test code, and observing the output as find out how the program behaves. What's the output? And once you understand what it's doing there, then you can dig into the details of the linked list functions and the node functions. So there's a class called node that naturally is used for the nodes in the linked list. It includes the data that you need to store in the node, as well as the pointers or the references to locate the next node and the previous node. Now, there's another aspect to the code here that may be alien to you, whether you're C++ or Java programmer, and that is the fact that the data, when you look at the node class, you'll see that it involves data with a capital D, and that's actually the data that's going to be stored inside the node, and it's set up to be generic. Okay, so generic meaning that at this point in the code, we're not specifying the type of data that's involved. This may be a completely an idea to you, but normally you'd have to say, okay, I want the data to be double precision floating point data, so I'll use the keyword double, right, to specify that. Here, we're not doing that. We're saying this is generic data. You'll find out later when we use the node class, when we create a node object, at that time, it'll be discovered what type of data to put in the node. Okay, so this is a nice feature that could potentially cause you a little bit of confusion, but don't worry too much about that. Look at the various accessor methods that are used for retrieving the data stored in the node. That should be old hat to you. Just returning the information that is stored inside an object. Okay, there are also some mutator methods, meaning methods that change the node, specifically to change the next pointer and to change the previous pointer. All right, these are very important methods that allow us to change what a node is pointing to, either in the forward direction or backwards direction. As already mentioned, when you remove a node, say, from a linked list, you have to change a bunch of pointers of other nodes. Also, when you insert a new node, you have to change a bunch of pointers. So these methods can do that job. Take a look. All right. Now there's the class linked list, which represents the entire linked list. Yeah, as I said, well, we're going to have one object created from this class, and it will represent the entire linked list. It has a first node, a first and a last. So there's pointer / reference in there to locate the first and the last nodes of the linked list. just as in the figure. And also, in constructing the linked list, it's going to be necessary to specify the type of data that is used inside each of the nodes. Okay, remember a moment ago we were saying that the nodes were set up to be able to handle generic data. And here, to facilitate that, we also have to put that generic aspect to things inside the linked list. Okay, if you look in the testing code, go down to the code that is used to test all of this stuff, and towards the top of the testing function, you'll see new linked angle brackets, and inside there it'll specify integer data. Okay, parentheses, parentheses. So it's actually what's inside the angle brackets that is finally indicating the type of data that will be stored inside the nodes, which in this example will be integer data. Linked list object also has a variable called size, okay, to remember how many nodes are in the linked list. There are accessor methods for linked list object. There are some methods for inserting new nodes into the linked list. So take a look at the linked list class, and you should be able to quickly spot the methods used to insert a new node into either end of a linked list. And there's also a method to remove nodes from either end of a linked list. You should be able to quickly spot those. And I really mean it. You really should go and find these things. Try to go through and make some sense of the details. When a new node is inserted or deleted, you'll see that pointers get changed around. Now, I'm not going to hide from the fact that this can be a little bit confusing at first. Let's take a look at some specific code. We don't have the time to look at all of it here, but we can at least look at the code that's used to insert a new node at the end of the linked list. We'll step through that in detail, and then I'm leaving it up to you on your own to similarly make sense of the other code. A tiny point here. I'm about to present the Java version of this code. The C++ version differs only slightly. The most conspicuous thing is that where there's a period used frequently in the Java code, there will be this arrow notation used in the C++ code. There are one or two other incidental things. So here then is the method from the linked list class that inserts a new node at the end of the linked list, right? It's also called the back of the linked list, right? So the start of the linked list is the front, and the end of the linked list is the back. Okay, this is responsible for creating a new node and putting it at the back of the linked list. There's a parameter D here, and D is actually the data that we want inside the new node. Okay? Let's quickly skip down and notice a couple places where it says new node parentheses D. So what does new node parentheses D do? Well, of course, it uses a node constructor you can find the code for the node constructor elsewhere, and you'll see that all this does is it copies whatever's in D into the data part of the node, and it sets both of the pointers to null. Okay, so the next and the prev pointers for this new node will initially be null. Okay, right, so the body of this insert at back method consists of this conditional statement. It does one thing if size is 0, and it does something else if size is not 0. So let's first look at size is 0. If size is equal to 0, well, that means that the linked list is empty at the moment, and what we're doing is inserting the only node into the linked list, right? When we get done, the linked list will consist of just this new node. So therefore it makes sense to have the first and the last pointers point to this new node. And that's what's happening here, where it says first is equal to last is equal to new node. That's identifying the new node as both the first and the last node in the linked list. And then after that, size is getting set to 1, indicating that there is now a single node in the linked list. And that's it. That's what it takes in that case. Okay, in the other case, when size is bigger than 1, when there are already some nodes in the linked list, then it works this way. If you can get past this next statement, the next couple statements. All right, this is the tricky part. Not going to lie to you. What we're doing here in this statement that says last dot set next parentheses new node parentheses D parentheses parentheses semicolon. We're creating the new node, and then we're arranging for the current last node of the linked list to have its next pointer set to point to the new node. Okay? So what is currently the last node in the linked list all has a next pointer which is no longer null, but instead points to the next node, the new node, right? The new node. And that's a big step in the direction of making the new node become the new last node. All right? All right. But so far we haven't changed last. So technically at the moment, since last has not been changed yet, the new node is not yet the last node. Okay? I know, it's tricky. All right. Now, the next line says last dot get next. Well, let's think about this. We just arranged for last to have its next pointer point to the new node. So basically, last dot get next is going to refer to the new node. Okay, it basically means the new node. And what we're doing now is we're calling set prev. Set prev is acting on what object? Okay, pause. Now this is it. Think about this. What is set prev acting on? It's acting on the new node. Okay? We're going to be changing the new node's prev pointer. Okay? I know this is a little bit mind-bending. Because last.getNext is the new node, we are now going on to change the new node's prev pointer, and we're changing it to point to last. Okay, we're changing it to point to the node that is currently considered the last node. The upshot of these last two statements is this. Before we created the new node, there was already a last node in the linked list. Now we've created this new node, and we want it to become the last node. All right, but before we can do that, we have to take the current last node and have it point to the new node, and also take the new node and have it point back to the current last node. We have to link them together, right? And as soon as we're done making that link, then we can change what is the last node. Then it's time to make the new node become the last node. And the way I'm doing that here is I'm reminding you that before we change last, that last.getNext refers to the new node. So the statement last equals last.getNext means that we're changing last to point to the new node. Okay? There's a lot to think about there. Now something simple. We've just added one more node to the linked list, so we want to increment size. And that's at least easy. Take the time and effort. I could completely understand if initially you're flustered, even panicked by those three statements above size plus plus. But see if you can't go through them carefully and scrutinize them. And the figure, drawing figures might help, right? I say again, the first of those three is for the purpose of setting the current last node's next pointer to point to the new node. The second one is for the purpose of setting the new node's prev pointer to point to the current last node. And then the third statement is finally to change which of the nodes is actually regarded as the last node in the linked list. Okay, the last node in the linked list will no longer be the node that was the last node. It will instead be the new node. So here it is again. Let me just quietly present these bullets so you can think about all this again. Okay, that was the Java code. I say again, the C++ code where you saw those dots, you're going to see these arrows, which consists of a dash followed by a greater than symbol. If you're familiar with pointer notation, then you'll understand what that means. I mean, it essentially is going to mean what we were just talking about. Okay. Okay, try to figure out what was just said as we looked at the Java code, and basically it's going to come down to the same thing in the C++ code. There's also a method buried somewhere inside that code to look for some specific piece of data in the linked list. It will sequence through the linked list. Starting at the beginning of the linked list, it will navigate. It will follow pointers and traverse its way through the linked list until it comes upon a node whose piece of data matches the data that we're looking for here. Okay? And when that happens, it will remove that node from the linked list. I'll tell you what, I would like you to find that method in the code, but you don't have to worry about the details. While it's okay if you don't want to look too hard at the the find and remove method that was just mentioned. I do want you to take a look at the display all method that's in the linked list class. It is a very short method, and I really think you need to look at all of this, okay? I think you should carefully step through and see exactly what's going on here. The purpose of this method is to display all of the data contained in the linked list, okay? So to do that, it traverses the linked list. Starting at the beginning of the linked list, it follows next pointers, and it basically hops from node to node, and each time it visits a node, it displays the data in that node. Okay? The exact statement that causes it to hop from node to node is this right here. Node is equal to node.getNext. And here's all it does. It's really pretty simple. This variable node keeps track of which node is currently being visited. Okay. And when you apply the getNext method to that node, you obtain the following node, of course, the node that follows that current node. Okay. Whatever the next pointer says. So node.getNext is going to be the next node, and this statement then copies that into the variable node. That changes node, and the effect is that we're no longer visiting the node that we were visiting. Instead, we've moved on, and we're now visiting the next node. Okay? And then all of that and the display and everything occurs inside a loop, and if you look at that loop, it simply loops how many times? Size, right? The nodes in the linked list. So when it finishes that loop, it will have finished traversing the entire linked list. Okay. Of course, you should make sure that you're comfortable with everything that was said conceptually concerning linked list. Make sure that all those figures make good sense to you. And then you ought to really scrutinize at least those portions of the code which are addressed here. As I just got done saying, take a careful look at display all, and then some of the other code that we looked at, and when you're ready, take the self-quiz.